They start out at night. A bunch of people set up their balloons and actually take off before they're on. Well, welcome and thank you for the invitation to come talk. My name is Zing Shiffman. I am a product marketing manager. Try not to hold that against me. I don't think of myself as one, and by the time we're done, I doubt you will either. What you will think of me as, we can discuss that. I am with Azul Systems, and what we do is going to be pretty obvious. I will do my best not to make this come off as a sales pitch. I will talk later on especially about kind of what we do. We do a Java virtual machine. It's designed for big server kinds of things that want to use a lot of memory. It fits right into the stuff I'm going to talk about, and we'll get that as we go. And by the way, we will leave some time for questions at the end. If you have something you just have to ask, we'll try to catch it as we go. And am I speaking close enough to the mic? Everybody can hear me. I'm not groovy. Okay, so hang on, let me get the slideshow going. I forgot to do that. All right, come on, first Alrighty then. Yes, that's me, that's the talk, that's the company, all that stuff. Right, so the interesting thing about Java is it gets used in all kinds of things. And for me, one of the things that's interesting is it's not being used for the things it was intended for, to the degree that anybody had a plan. Probably the biggest use of Java is on servers. J2EE was all about wiring together components to implement business rules. It was also getting heavy use in kind of distributed computing, big monolithic kind of compute jobs, things like that. I actually worked for a couple of companies who were doing grid and cluster computing in Java before I joined Azul. The funny thing, of course, is so use in the client, not nearly so much, but that was the thing that got all the attention. If you remember, right around 1995, when Java went public, it was because of something called the Hot Java browser. It was not just that you used Java in a browser, but there was an entire browser written in Java. And people got all excited because they were excited because browsers were new, HTML was new, and then people discovered, oh, you're not talking about a language like HTML, you're talking about an actual programming language, and I don't know how to do that. And people lost interest pretty quickly. But that was the way it was pitched was, this was going to be for browser kinds of stuff, and you still see a lot of that today, but not nearly as much. I mean, how many people here see Java in their browser on a regular basis? Show of hands. 1, 2, okay. Yeah, that's about what I would expect. You do see some interesting stuff being done in big client-side applications, fat client applications using Java, especially in the financial world. There's some of that going on because it is a great language for building those things. They can throw a lot of horsepower, they get good performance. And of course, Java has really taken off recently in the embedded world through this thing called Android and this thing called Dalvik, which courts have decided is not exactly Java, even though it kind of is. And so you have this whole embedded world of people building applications in Java on smartphones based on Android. Why has Java got such appeal? And by the way, I'm going to get to the good stuff fairly quickly. I just want to make sure we level set. So one of the things was that it was portable. It was this whole idea, the promise of write once, run everywhere. Of course, you still have to test everywhere. Anybody who believes that you can write it once, test it once, and it works on any platform, well, I got some bridges you really love. It's productive. Now, I came out of the Lisp world years ago and then moved to C++. I told a lot of Sun Microsystems engineers how to program in C++, moving from C. And so one of the things about C++ was it had a lot of really awful features. I would argue, does anybody want to argue, raise your hand if you think I'm wrong when I say that operator overloading is a terrible, terrible feature. Anybody want to argue that point? Okay, cool. The problem with it is it can be abused horribly. There's simple cases where it's useful, where a plus operation makes sense. But I'll give you the example of I worked at Borland very briefly, and my manager wrote the Borland C++ for Dummies book. And to demonstrate object-oriented programming, his object class was a pizza class, which is kind of fitting, given things. And he defined a casting operator to convert a pizza to an integer. Does anybody want to guess what that did? Anybody have an idea?
The number of slices.
Number of slices, that's good. No, that wasn't it. Anybody else have an idea?
Diameter.
Diameter, that's a really good one. No, that wasn't it either. I thought about price. That wasn't it. His answer was number of toppings. And not only was that a bad answer because it's no better than any of the others, but it doesn't actually work outside the US because people order pizza by style, not by number of toppings. But the whole point was, and the other case I ran into was the first C++ class I took. The instructor defined a plus operation that modified the left argument and didn't return a value. Because C++ doesn't keep you from doing dumb things like that. And what's the one thing we understand about plus? Right? You know, we know that it doesn't modify its arguments. We know it returns a result. We know that the order of the two arguments shouldn't matter. But you're free to violate those things. So operator overloading was a terrible idea because you can look at the code and you have no idea what it does, unless it's a very simple numeric type. Multiple inheritance is terrible for all kinds of other reasons. I came out of the Lisp world where we used it a lot. It was a terrible idea, and of course Java avoided both of these. So from that standpoint alone, it was wonderful. The other thing was Java has a do the right thing philosophy, and C++ didn't. C++ had a philosophy of that no feature should cost me in performance if I'm not actually using it. So you could write as efficiently as C, but that meant that you had no idea how people's code was going to work because were things declared, you know, where they defined it compile time or at runtime, you really didn't know, you had to go back, you couldn't just look at the code and know what was happening. And Java was a lot smarter about this. And of course, memory management in Java reduces a whole lot of opportunity for error. It lets us do a lot more work that's useful and not spend a lot of time tracking down bugs because we forgot to release something that we allocated. These are all really good things. Another thing is that Java has become amazingly efficient. It started out as just an interpreter, just a bytecode interpreter, and then we had just-in-time compilers, and now the state of the art is dynamic compilers and decompilers that will take, that will inline method calls, and then it will look at how they run and decide, well, that wasn't really worth it, I don't want to do that. It will uninline them and recompile the code as it goes. So you really can be more efficient than languages like C and C++ because it knows how the code's being used in a way that statically compiled languages don't, which is pretty darn cool, something I didn't see coming. When I was at SGI, I got to do a lot of Java contrarian talks. And so this is the kind of thing I talked about, and of course, over the course of years, a lot of what I said was no longer true. That was true when I said it, probably. The other thing is, Java is generic. It's not about the Java language anymore. There are all these other language systems that are taking advantage of the Java virtual machine, that environment. Things like Scala and Clojure and JRuby and all kinds of other things. They're using that as their runtime. Now, back when I was at Sun, there was this organization called the Open Software Foundation. Anybody heard of that? I see at least a couple nodding heads. And at Sun, we thought that OSF stood for Oppose Sun Forever, but that was obviously the way we feel about it. One of the things they were trying to push was something called ANDEF, the Architecture Neutral Distribution Format. The idea that your compilers would compile to a generic sort of bytecode, and then when you got to a targeted machine, then it would do the compilation of the actual machine code based on what it knew about that machine. The pipeline size, number of processors, whatever the heck it was. It didn't catch on. I would argue that Java is ANDEF. It actually has that, satisfies the desire that existed back in the very early 90s. The other thing is that Java is very scalable. As we said, we see it in smartphones, we see it in big server applications and big compute farms. I mean, one of the companies I worked for was doing 20 or 30,000 CPUs all in a centrally managed grid. That's a pretty big environment and it's all Java, although you could write your application code in something else. But how scalable is it really? This is something our CTO does when he gives a talk that I stole most of this stuff from, just so you know. So here's what I want to do is, how many people here know how big the Java heap is that you use in your applications? Show of hands. You're going to be able to answer that question. So a few of you, okay, not as many as I would like, so this is going to be not quite as exciting, but I'll explain where we're going. So, for those of you who do know, how many have more than half a gigabyte in your heap? Yeah, everybody. Okay, 1 gigabyte? Okay, keep your hands up, and when I get past it, you can drop it. 2 gigabytes. Lost a couple. 4 gigabytes. Lost more, down to 1. Wow. 10? 20? 50? Cool. Oh, that broke out. How big?
Yeah, it's 42.
42. Of course, I should have known that answer. Okay, so we don't have to go through the others. And the interesting thing is, every audience you ask, the answer will always be the same. The vast majority of answers will be 1, 2, 4 gigabytes. No bigger than that. And that's really interesting. And the reason it's interesting is because Parkinson's law applies just as well to software as it does to everything else. And Parkinson's law is work expands to fill the time allotted. Work expands to fill the space allotted, the resources, everything. And hardware is growing, transistor counts doubling every year and a half, memory size growing about 100 times every 10 years, and application size, and these are the size of an application where you wouldn't bother swapping it out to disk. And you can see that, decade by decade, the number increases by about a factor of 100. So in 2010 or so, we should be around 100 gigabytes of data that we're playing with. And yet Java people are still working in the 1, 2, 4 gigabyte range. Anybody want to tell me why?
Memory efficiency. The default.
What's that?
The default? Was it?
Well, I'm sorry, I didn't catch it.
Default.
No. You can specify bigger, but people don't. Yes?
Is it because everybody's using commodity servers and clustering them together and just being cheap?
But why? Here's the thing. This is what a server costs these days. Huge numbers of cores, huge memory are cheap. These are your commodity servers. And so what that says is Java people are using a couple of % of the typical server you can buy today. These are Dell prices. Yes?
The problem with your analogy, though, is that if you're an individual, 5K is a lot to spend on a computer. And if you're a bean counter, what are you talking about? I'm going to give every developer a 5K box.
I'm not talking about developer boxes. I'm talking about the boxes applications run on.
Right, but if the developer doesn't use it, it isn't going to get used.
Well, that's an interesting question, but I would argue there's a much more
16 gigs
yes.
is 100 bucks.
Well,
Come on.
I'm finding that 1.5 gig is the optimum size because garbage collection stops the world.
Yep. Thank you. I knew somebody would say it if I problem. Yeah, the problem is that Java's memory manager has a scalability. It doesn't do very well for certain classes of applications. So let's look at that. Here's the thing. This application, this is basically EH cache. It's an in-memory cache. I ran this on a Linux box in my cube. Cache is 10 gigabytes in size. The heap is 29 gigabytes. That's as big as I can get on the box I have. And it's a 48 gigabyte machine, 16 cores. And what you're seeing here, this is a tool I'll talk about. It's a free thing that our CTO wrote called JHiccup, and it lets you see stalls in your application. And these are related to memory matches. What you're seeing at the top there is that the worst stall, and this was on Hotspot, the worst stall that this application saw was about 8.5 seconds. And I'm assuming, and kind of verifying, yeah, that's garbage collection. Okay, not 1% of the time it was at least 5.5 seconds. That's the delays you're going to see with the heap that size, with the 29 gigabyte heap. And this gentleman here with the 42 gigabyte heap, is that a batch application or is that interactive?
It's interactive and it doesn't have garbage collection closes more than half a second.
Okay, great. And I'm imagining that took a certain amount of tuning to achieve.
Yes.
Okay, good.
And I would blame unsatisfactory exposure of the unsafe class in Java. So
Okay.
I cannot use.
So this is the thing. This is a pretty typical sort of response in Java once you get above a certain size heap. And the interesting thing about it, oops, I think I moved my mouse somewhere I shouldn't have, so let me just The interesting thing about it is this is a response curve based on service levels. So what it's saying is that on a percentile basis, how often does it get bad? And so I would say, you know, I have an application that has to respond within this amount of time, and what percentage of the time does it violate that? And now you can see that there's my 99th percentile where I'm about, not quite 5 seconds. And there's my worst case at the end where it's, 8,600 milliseconds. And that's a pretty common thing to see with an application of this size. Okay? And the important thing about this is people think of response in terms of averages and standard deviations. They think in terms of bell curves. And Java stalling, because of memory management, does not fit a bell curve. Standard deviations are meaningless. It just doesn't fit that.
Can you explain this chart here?
Sure. So this chart is basically saying, so these are times mapped against percentages of the run. So it's basically saying down here, 90% of the time we were under a second. And we were less than half a second. So you see what that's
response time to your server?
Well, okay, so what we're showing is this is strictly the time the application wasn't able to run because garbage collection had frozen it out. So the way this works, just to give you an idea, is it's a little agent you drop into your JVM, and at every 1,000th of a second it wakes up, does a tiny bit of work, and then measures how long it took to do that tiny bit of work. And the idea is if it took longer than a tiny amount of time, it said, oh, I wasn't able to run. So if it took half a second, it said, obviously I wasn't allowed to run in that half second. And then it graphs that. So it's looking at what are those stalls? How long are they? How often do they happen? And so if we go back to the previous picture, what you're seeing are each of these things is probably a garbage collection event of different sizes. So every time it goes, it's basically saying the application couldn't run. So this is time to add to what your application is doing, that the application didn't get any work done because it got frozen out by the memory manager. I'm assuming. And in this case, I know. Okay. So this is the thing. We start with this assumption about response time, that response time relates to load. That if the load is low, we are going to get what we think of as a good response. And as the load increases, the response times get worse. Right? Everybody's sort of comfortable with that idea. That's the way we're used to thinking about this. And when the load gets too high, then it all goes to hell. Response times get really, really bad. That's not the way it works in the Java world. We get something more like this. And what you're seeing here, if you see that light blue kind of line, that's load. But you see those spikes, the black ones with the little arrows at the top? Those are stalls. The response time was really bad, and I'm assuming that a lot of it was because of garbage collection. But the way garbage collection works is, if my load gets higher, my GCs may become more frequent, but they're not going to become worse. That's related to something else.
To be clear, is this observed at the process level? It's guaranteed to be on machine and not something below that in the network stack or something?
That's right. Exactly right. Yes. Yeah, we've eliminated that in this case. And actually, in the that's the important thing, is that the way JHiccup works, because it's only doing its own work. It's basically, if it can't run, it's because the JVM wouldn't let it run. And if you've got enough cores, that shouldn't be a problem. By the way, it works on any JVM you care to throw at it. That's the thing, it's not specific to what we do. It's just, you can drop it into Hotspot or J9 or JRock or whatever and play. And it will show you. Yeah.
True garbage collection, I guess in your case it's so small, you only one of that.
Well, absolutely. Yes, I mean, if for example, there was a garbage collection with a big heap and it took minutes, you would see a spike that way.
But then you won't get another garbage collection while you measure.
No, of course not, because
there's a lot more.
You can't run multiple garbage collections in parallel. It's freezing everything.
No, I mean, like, you start some processing, you end it. You got one garbage collection, but they're not going to get a second one before you end it.
That's possible. It all depends on how your application uses
But
it.
in your measurement, you only get one.
Oh no, you see, we had a bunch. Every time you see I'm sorry, I'm going the wrong way. Every time you see a spike here, that's another garbage collection event. Even these little ones are all garbage collection events. Those are probably new gen. So there are lots of them. And some of them will be huge and some of them will be really small. But that's the thing, it's like they're affecting the application performance. Okay, so let's talk about, some things we can sort of agree on about garbage collection. First of all, it is really, really efficient. It's actually more efficient in terms of doing its work than doing mallocs and frees. It does things very, very efficiently. If you have a bunch of objects you're no longer using, it costs nothing to collect them and reclaim the space. And it is true that the garbage collector will find all the objects that you're not using anymore. You can't fake it out with, cyclic graphs pointing back on themselves. It's still going to find everything. It's still going to reclaim. Those are the good things, but there's some bad things. First of all, you can count on a garbage collector with modern processors to stop things for about a second for every gigabyte it has to reclaim. Live objects that it has to go through. So the stuff that's still in use. You can change when a GC will happen. You can't get rid of it. Okay, I lied. That's what we do. We'll get to that. But basic GC, yeah, you live with it. You can still have memory leaks. Anybody here ever had a memory leaking job? Yeah. You have a memory leak because you're holding on to stuff you didn't need to hold on to, didn't realize you were doing it. Obviously, it just gets held on to until you finally get rid of it, if you ever do. So you can still run out of memory. Most people will do a run for some amount of time, and they won't see any stalls for garbage collection, and they think they've solved the problem, and they probably haven't. They've just pushed it, kicked the can down the road a ways. You run it for 20 minutes, maybe it happens on the 21st. You run it for 3 days, maybe it happens on the 4th day. You really can't get rid of them except doing some fairly arbitrary things, and even then, you're not really getting rid of them. Okay, how do garbage collectors work? There are 3 phases that they go through. They all do this. They may not do it as separate phases, but they all do this. Basically, figure out what you're still using. Start with your stack variables on the stack. Start with all your static variables and go through what they point to, what they point to, what they point to, marking every single thing you see until you run out of things that aren't marked. So that's phase 1. Phase 2 is to somehow reclaim all the stuff that you didn't catch in phase 1. Okay? Basically, anything we didn't flag is now garbage. We can reclaim that space. And that's often done just by making a record of, okay, I got free space from this object here, or these are next to each other, I can reclaim that space, great. And then the third thing is, you have to defragment at some point. That's the third phase is, I got to crush everything together so I can have a big open space for my objects, because otherwise I'm not going to be able to create new objects because I don't have the space big enough. And so you relocate the defragmentation operation, and then you have to correct all the things that are pointing to those objects to point to them in their new location, which we call a remap operation. All right. Pretty standard is that your old generation garbage collector, the big one, is exactly those 3 phases. It marks, it sweeps, it compacts. Which was the vacuum cleaner that beats it as it sweeps. Right, so that's what it is. It's 3 separate passes, and the great thing about it is it doesn't need a lot of extra heat memory to do its thing. It's kind of in place. For new generation, we use a copying collector. As we flag an object, we move it to a duplicate, another memory area that's as big as the one we started with, and when we're all done, we can throw away the old area and just use the new area. It requires twice as much heat, but it's very fast. We can do it all in one go. This generational GC is a really interesting thing. I was working for a company called Symbolics. Anybody ever heard of them? Okay, I see a couple of them. Right, and it was a company that made list machines. Something that was really exciting in the great AI boom of the 1980s, and as soon as DARPA stopped funding AI, that sort of took care of things. And the idea was that, so they had garbage collection, kind of like what Java has, and there was a guy named David Moon who invented what he called the ephemeral garbage collector. He wrote a paper in August of 1984, I believe, about this technique. And the whole idea is that most objects you create are going to become garbage really quickly. And the great thing is, because of that, if we can reclaim that, we're going to get a whole bunch of space back for minimal work. And that's the whole idea behind this generational thing is, so we use a copying collector on our new objects. We can scan a tiny percentage of the heap. We don't need much space for, to move the objects that survive. There's not very many that will. We reclaim a lot of space, very little time spent, very little effort. And any object that survives a few of these new gen GCs, we say, okay, it's now old, move it to the old area, and it won't get collected very often. Very, very efficient. Eventually, we have to go in and we have to look at the old generation because the new gen collections aren't finding us enough stuff, and we do the old gen. It's much less frequent. The cost is a lot higher because you're looking for a much bigger memory area. The benefit for the effort is a lot lower, but you have to be. Now, new gen requires this idea of a remembered set, and it's usually implemented through something called card marking. Because here's the thing. Remember when I said that the way the garbage collector works is it starts with all the variables on the stack, and it starts with all the static variables. But if you're looking at the new gen area, what you need to know is where outside of new gen are there pointers to something inside new gen. And so you have to keep track of that. The way they do it is through this idea of card marking, of keeping a bit table or a byte table or something of every place that has such a reference or had one at one time, and then we go through it and we say, does it still point to new generation or not? Because if it does, then we have to change what it points to point to the new location when we move the object. So that's extra overhead that we have to do. And so the idea is that it's not just the stack and the statics, it's also any place in old gen that points to something in new gen. And if we're doing multiple generations, we have to keep separate of those remembered sets for each generation. And it's actually true that even though I said, and most people will agree, that new gen needs double the memory space so that you can copy, in case you have to copy over everything, you don't actually have to. If you were really tight on memory, you could just shove everything that survives into old gen. Won't be as efficient, but it'll get you past that problem. So if you're really tight on memory, they can use that as a way of getting through that. Okay. Little terminology, just so to make sure we're all using words in the same way. By the way, that's one of the things, and I have done jobs both in marketing and sales support and things. It's like the biggest fallacy in the computer industry is the idea that we have a common terminology. And so I would describe previous companies' products, and they say, "Oh, is that grid?" And I go, well, "Okay, I've got 4 different definitions of grid. I'll tell you what they are. You tell me if it's one of those or you got another one." But, so I want to make sure that we're talking about the same thing because the words matter. So the idea of concurrent versus parallel. This is very important. A concurrent collector allows the application to run while it's garbage collecting. A parallel collector simply is doing multiple garbage collection operations in parallel. And the important thing about that is you could have a collector that is parallel but not concurrent. You could have one that is concurrent but not parallel. You could have one that is both. You could have one that is neither. It turned in the very early literature about Java, they use parallel to mean concurrent. But it's been a long time since anybody's made that mistake. There's a general agreement. When you say parallel, you actually just mean multiple threads doing garbage collection. When you say concurrent, you actually mean the application can run. Another term, this idea of concurrent versus stop the world. That's pretty obvious. A stop the world collector doesn't allow the application to run for some period of time while it's doing its work. That's why we see the stalls. And as I said, a stop the world collector might be parallel, but it is not concurrent. If it was concurrent, it would be stopping the world. And incremental. One of the ways to get around long stop the world pauses is you do it incrementally. You do a chunk of the work, and then you let the application run, and you do another chunk of the work. They're probably stopping the world, but they try to stop it for less time. And the idea is to let the application run enough that you don't notice the delays. The delays are there, but they're small enough that you can meet your service delay. The other thing, and this is important, is this idea of precise versus conservative. So if I was building a garbage collector for C++, God help me, I would probably have to build a conservative collector because I can't know if every single variable I'm looking at, say on the stack, is a pointer or an integer because they look the same. Just a bit pattern. And so a conservative collector, if it can't know which are, that every single pointer is a pointer, then it can't relocate objects because it can't change them to point to the new location where the object moved. If it knows, then it is a precise collector. That's what you have to have if you want to be able to relocate and defragment. That requires that the compiler record information about what kind of thing it's got, whether something is a bit pattern or an actual pointer. Java, of course, is a precise collector. It knows every single thing. Is a pointer or not. And the other important concept is the idea of a safe point. Basically, places in the execution of your application could be a single code location, could be a range of addresses, where the collector can figure out every single reference in the thread stack. That means I can do a garbage collection. Because I know that they're there and it's safe, I can make changes, and I'm not going to break anything. So the idea is you get a thread to a safe point, and that's when you say it has to stay in the safe point while I do a garbage collection. Which might mean pausing the thread, it often does, but not always. For example, if you're in the Java native interface, people who use JNI, okay, just a couple of you, if you're using native code, as long as you don't refer back to Java objects, that entire time you're in the native code, the garbage collector is in a safe, it's in a safe point, so the garbage collector can do whatever it wants. You need to have lots and lots of safe points, otherwise you can't garbage collect and you might run out of memory. So you have to have lots and lots of them. There are also these things called global safe points, where all the threads have to reach a safe point at the same time. You have to wait for all the threads to come together, which could take a while. That gives you a whole different kind of stall. Not when a garbage collector is running, but when a garbage collector is waiting to run, and it wants to block all the other threads until that last one gets there. Okay, so the typical thing, as I said, is you've got new generation. Typically, it is a copying collector. Typically, it is monolithic, stop the world, do everything in one, and then let the application run. Old generation typically is going to be mark, sweep, compact. It might stop the world. It might be concurrent. It might be mostly concurrent, by which I mean concurrent most of the time, but not always. It might be incremental and stop the world. It might be mostly incremental and stop the world. Yes?
When would it not be safe to do garbage collection as far as the thread? What is the thread doing that makes it unsafe to do garbage collection?
Well, basically, the problem is, once you get into a garbage collection, depending on how it's written, it may not, if your application is mutating pointers, basically,
Java, you can't do that. Right?
What's that?
But in Java, you can't do that, right?
Well, the point is right, but if you can't do that, then the application can't run until the GC is done. So the whole point is, the application, so threads will basically reach a safe point in the code. Basically, in the interpreted code, in the compiled code, there are places where it says, right, I'm going to decide this is a good place to stop. Now, if you don't allow them very often, if the Java virtual machine doesn't allow them very often, then you can't garbage collect for a long time. JVMs run into this, especially in the early days. It might be hundreds or thousands of instructions before it gets to a safe point, which means if you've got multiple threads and you're running low on memory and the GC wants to run, it has a choice. It can either allow all the threads to run and maybe they run out of memory, or it says, I'm running low, I'm at a point where I need to run garbage collection. I'm going to stop the threads as soon as they reach a safe point. But that last thread doesn't reach a safe point for a while. It's doing a bunch of operations. So the important thing is you design your JVM so they reach safe points pretty frequently in time. Because if they don't, then you're stuck.
As you write the application, is there anything you can do to increase those safe points though?
Not really.
Have anything?
Not so much. Yeah, and I would argue you shouldn't, even if you could. Because we shouldn't be worrying about this stuff in our applications. The whole point of using high-level language is not to deal with stuff like this. Okay. So the important thing is the word mostly, we mean not always. Every single garbage collector, I'm lying again. Most garbage collectors have a fallback to a stop the world collection. And when that stop the world happens, your application freezes, potentially for a long time. And what a long time means entirely related to your application. Okay. I'm going to tell you a little fable, except it's not a fable, it's real. We call it the good little architect. Now, the important thing to understand is, if you're a real architect, you must be able to impose your architectural decisions on your development team. If you're not, you're just a philosopher. So, and I say that because here was an architect who made some decisions. Now, we started out doing Java appliances, boxes that ran in Java, dedicated boxes. And we ran into an application that had an 18-second pause. And we'd never seen an 18-second pause before because our whole point was to not make those happen. And we ran into it. What we found out was the application was doing tens of millions of finalizations every time an old gen GC happened. Everybody knows what a finalizer is, right? Anybody doesn't? Okay, good. Right. And the problem was in our JVM, reference processing was a stop the world event, and we didn't expect there would be tens of millions of them all happening at the same time. So there were all these finalizers. Every single class had a finalizer. Anybody want to guess what it did? What's that?
Nothing.
No, it did something. If it had done nothing, we wouldn't have had a problem. It did something. What it did was null out every reference in the object. And the problem was that meant it was mutating the object, which meant the garbage collector had to go back and survive another generation, and all these things happened. The theory was they were trying to save the garbage collector from having to follow those pointers to the other objects, which bought you nothing. The reason that they were doing that was, I'm guessing that the architect came from the world of C++ or Smalltalk, where they do reference counting. And if you're reference counting, you have to make sure that the count gets decremented, and then when it goes to 0, now you can reclaim the object. So for C++, if you're doing reference counting, that's all cool. That's fine. In Java, it's a disaster, precisely because in this particular implementation of the JVM, finalizers had to get executed, and they would look at this stuff, and objects survived a little longer. And going through all those, so many of them, all those finalizers had to run, and they actually did something, so they actually had to run that code. Here's another example. We've run into people who have objects that reference file pointers or network connections, things like that. And rather than closing them when they're done with them, they'll put the closing code in a finalizer and they'll just throw away the object. Now that doesn't seem like a horrible idea until you realize that right now you may have a couple of hundred open file connections. But someday your application may have 10,000 of them, and now you're tying up all these operating system resources until the end when the garbage collector runs. And now the operating system is racing like mad to keep track of it. And the problem is that things change at scale. They get worse in a big way. How many people ever learned to do a bubble sort? Most of you, right? Bubble sort is really easy to write and it's fun. And if you only have like 10 or 100 or even 1,000 objects these days, it won't take that long. So just think about what happens when you have a million. It's horrible. And that's the thing, is people don't necessarily write code with the understanding that someday the stuff they're doing will get 10 or 100 or 1,000 or 10,000 times bigger. So there are two morals to the story. One is you have to know the cost of your actions. There's an old joke, not funny, but it's old, that because in Lisp, as in Java, everything, pointers, you don't see pointers, you just follow them, you see the thing they point to. And so they'd say that Lisp programmers know the value of everything and the cost of nothing. You have to know the cost of things, at least at some level, to avoid doing things like this group did. And the other thing is, as I said, just because it's not costing you now, it doesn't mean it won't somewhere down the line when you're dealing with far more data than you are today. Yes?
So the problem with not clearing the references sometimes is that if you have a very large cyclical graph, and you don't control every single element of it, which has happened to me, I was using a third-party library that kept one reference to the cyclical graph in a static variable.
I feel your pain, as Bill Clinton once said. One of the things we built into our VM just recently was something you could use at runtime for memory leak detection to figure out where those things are coming from. So you could look at it and go, what kind of objects do I have that are taking up all the space, and who points to them, and get down to what classes of objects are doing that, so you get a handle on why that's happening. But yes, absolutely, and the answer was they shouldn't have done that for exactly the reason you said. But the reality is that, I mean, it's going to hold on to the memory, and that's true, and that's a problem, but it's not going to slow down garbage collection particularly, because once it gets through that graph the first time, it's painted and it's done.
Well, except that it was doing it on every single window, so we were losing 4 megabytes of memory every 10 minutes.
Yep, absolutely, and that's a memory leak problem, and yeah, you can still have that if you don't code well. Yeah. I agree. You know, it is a real problem. Java doesn't give you a great way around it, but there are runtime tools that can at least help you identify where they are and figure out what to do about it. But that, of course, is a problem of using third-party libraries to do things like that, which is the other reason that having a rule that says, this is how I'm going to manage memory, could cause a problem because not every library you use, every tool you use, every piece of code you use is going to follow those same rules. You can't enforce the discipline everywhere. Okay, so let's talk about how garbage collectors actually work in the real world. So Hotspot actually has 3 garbage collectors, 3 different GCs you can choose from. First one is called Parallel GC. Remember what I said about parallel? So, new generation, it's monolithic, stop the world, it's a copy and collector. Old generation, monolithic, stop the world, mark, sweep, compact. Faster because it will use multiple threads if if multiple cores are available to divide up the work. It still freezes the application for the entire length of the old Gen GC. And by the way, the graph I showed you before, that was from Parallel GC. That's the default. Second one is called Concurrent Mark Sweep. Can be much better. Can be much worse. The way Concurrent Mark Sweep, the new Gen garbage collector is exactly the same. I don't know if it's the same code, but it operates in exactly the same way. Monolithic, stops the world. Again, assumes that it's a small new gen, therefore that won't take very long, so that's fine. Old gen is mostly concurrent, non-compacted. So what it's doing is, it's finding all the free space, it's making a linked list of all the free space. It is not crushing it together. It will not defragment, unless it absolutely has to, and then things get very bad very quickly. No, they get very bad and they take a long time to be very bad. Okay, so the idea is, it does mostly concurrent marking, so it does it in multiple passes if it has to, so that it doesn't take too long. It will do the sweep concurrently, because it can do that. So we'll find all the stuff and make a big list of all the holes from objects that are no longer there. It will not compact. And eventually, when it runs out of space, you can't go any further because you don't have a space big enough for this object you want to create. Then it'll do a monolithic stop the world mark sweep, just like Parallel GC does. I have no idea if it's actually parallel in that case. Interesting thing. No, I lost my train of thought. Okay. So that is a second option. The third option is new in Java 7. It was available kind of experimentally in Java 6, and this is called G1, or the garbage first garbage collector. Same new gen we've talked about. The old gen is a mostly concurrent marker. It does stop the world so it can catch up if the application is mutating, is making changes to references. It has to go back and look at them and see, did that change its concept of what's garbage and what's not, where things are. It has to do reference processing. It has to do those remembrance sets I talked about, the card marking thing, because what it's doing is it's working in separate regions, and so it has to keep track of pointers in one region, pointing to objects in another region. The compactor is mostly incremental. Stop the world, so it will do a chunk at a time, freeze the application, but maybe not for very long. It looks at the regions and figures out which ones is likely to be able to do in that limited amount of time. So it has a concept of heuristics that say, here's how long I should spend doing this, and so I'll pick my region size. It will actually avoid objects that seem to be mutating a lot. Until it absolutely has to, that fallback, stop the world collector kicks in. Okay, well let's think about this. Why or when do pauses matter? When does any of this really matter? Well, first of all, interactive applications. How many people are doing interactive kinds of things in Java? Okay, quite a few. All right? You know, you've got a transaction, you've got a customer out there, the transaction takes a second and a half, maybe takes a fraction of a second, that would be good. And now you've got 8 seconds of additional garbage collection that throws out a transaction every now and again, and that's a customer you've lost because they're not sticking around. That's not good. But if you're doing batch applications, you probably don't care. Because all you care about is start to finish time, and this is no worse, maybe even better than something that was better at transactions. Big data applications. There are lots of situations where I would argue it would be great if you could have lots and lots of memory. Classic example is you're doing a travel site and you want to maintain the inventory of hotel rooms that are available in major cities. Because those questions come up a lot. You want to keep it in memory, but if you do that, now you've got a huge memory space to reclaim, and that's going to take time. The more memory you have, the longer GC takes. Another example, and this is a real one, you want to do search. And you want the index in memory because that's the fastest way to do search, but your index is big. We actually there's a guy on the Lucene project who took the entire Wikipedia English language index, put it into memory. I'll show you some data from that in a bit. You could argue that there are benefits from an efficiency and management standpoint because you could have a smaller number of much larger JVMs to do the same work. You could probably get much more efficient because, of course, you're not duplicating all the code and a lot of other stuff across lots and lots of little instances. And managing them is a little easier if you've got 5 instead of 50. Stay in the same box. And the boxes are big enough, you might want to run 50. The other thing is there is a world of low latency. These are folks like in the financial world where they're processing data. They've got a data feed of market data, and they have to process it as it comes in. If there are a couple milliseconds longer than they've got, that's a disaster for them. And so their requirement is measured in small milliseconds, maybe even in hundreds of microseconds. And believe it or not, some of them are doing this in Java. Okay? So it also requires that they're running on a low latency operating system because now it becomes scheduling events and other things become a huge issue. So everything down the stack has to be very efficient as well. Very predictable. Okay, so garbage collector pauses. How often you see a GC relates to the rate at which you create objects and the rate at which your application changes them, modifies them. The severity of stalls relates to memory size. Okay, the more stuff we have to look at, the longer the GC is going to take. The more we have to examine, the more we have to copy. So our live set sizes. Or when we're compacting, the amount of stuff we have to compact. New gen is usually not the problem because we keep new gen small. But if new gen is 1% of old gen, and now old gen is 5 terabytes, we're going to have a problem. So in most cases, it's not how much garbage collector overhead we have, it's the fact that it all happens in one big chunk. So if we could just break it up in lots and lots of little pieces and slow down the application time, maybe that'd be okay. So, what is the GC overhead? Well, it really depends on how much stuff we get back. The worst case is our entire heap is live objects, and we run the GC, and we get done, and we haven't reclaimed anything, and the GC starts all over again. We're spending 100% of our time garbage collecting, no time running the code. This would not be good. Best case is we have infinite memory, and so we can just keep creating objects and the garbage collector never gets called. And of course, everything in between is kind of a 1 over X curve. So the important thing is the bigger our heap, the lower the percentage of time we spend garbage collecting. And if it didn't all happen at once, that would be okay. So, this goes back to, okay, so you have to figure out what the problem is and how bad it is. And that's why I talk about this thing called JHiccup. If you go to jhiccup.com, you can download it. It's made freely available, sources there. It's all open source. Do what you want with it. You can see how it works. We haven't snuck anything in there. And what it basically does, as I said, is you run it with your application, with your JVM, in your JVM. It does minimal work and it it records how long it took to get back from that minimal amount of work, and then it lets you graph it. If you see a long delay, it's indicating that for some reason the Java virtual machine was not allowing the application to run. What it won't show you is bad code. It won't show you an inefficient output. Yes?
So what if you have, is there any way of telling JVM that this is something once created will never go away?
Sure, permanent. Declare it as part of the permanent generation.
How do you do that? How do you do that in the language?
There's something. I mean, there is a mechanism. I don't use it, so I couldn't say. But there is a concept of a permanent generation that you can.
And that takes it out of the word speech space.
Yes.
Classes by the class loader usually get loaded up into Concurrent, and that's in fact the classic thing you run into with Spring applications and other like Maven type applications, where you load a whole bunch of libraries and stuff. I think by default it has 32 megs to 64, which is nowhere near enough. So usually you need to up that.
Usually, yeah, yes, that's why I love yourself.
But I don't know if you can how to do it programmatically.
There is a low-level mechanism that allows it. Whether they expose that to typical programmers, I don't know.
Don't Spring have a method that allows you to put it in the current?
I think they do, yeah. And that's the thing, is right. So there are mechanisms for doing that. Okay, so the important thing is, as I said, this is not going to. If you don't see a stall and your application is running badly, the problem is in your code or something higher up. It's your network connection, it's your database connection, it's something else that's outside the JVM. This is only showing, so it's basically showing you all the times that JVM wouldn't allow something to run, not that your application couldn't run for other reasons. And, so you run it against your application, and then you can also run it against an idle JVM, and if you see stalls then, it means you've got something below the JVM on the stack that's causing a problem. Power management, VMware or Zen, something at the operating system level, yeah.
So is JVM an instrumentation tool, or is it a performance testing tool where you can use it to simulate?
No, it's not. No, it is absolutely not that. It is simply a measurement tool. Okay. That's all it is. Is basically it does exactly what I said. Every 1,000th of a second, it wakes up, does a tiny bit of work, records how long it took to get back, and puts that to a text file.
Is that something you can do in production too, or is that just for the code?
Yeah, you can do it in production. It's incredibly. You won't notice the overhead unless you're doing low latency stuff where you'll notice anything. A fly buzzes through the room will affect your application. Yeah, so absolutely, yeah. I've run it and I've not run it, and I can't measure any difference in the execution on some heavy load. So yeah. So you can, if you run it against an idle JVM, that'll tell you if it's below, because you don't want to spend your time trying to debug performance problems in your code if they're not in your code, or in your garbage, in your memory management if it's not in your memory management. There are all these other things it could be, and this gives you a great baseline for understanding where the problem is and how bad it is. Again, if you see it on an idle JVM, that means you need to look at your OS, you need to look at what services you're running. Maybe you've got cron jobs that are kicking in every now and again, and you don't have enough memory for everything to run well, or not enough cores, or lots of things. That's the lesson, okay? You don't want to fix things until you know what the problem is. And that's the important thing. How many times do people, immediately go, okay, I have a problem, and I started to try to solve it. So if you didn't even figure out what it was, you're throwing darts. Okay, so what can we do about pauses? Well, there's the marketing solution, which is to use creative language. Okay, these are actual things that people have said. For example, I can guarantee a worst case of so many milliseconds 99% of the time, basically saying it sucks the other 1%. If it runs for 2 weeks, then that means it's stalling for several hours. That's probably good. Mostly concurrent, mostly incremental. I think you can see what the problem is with that. Fairly consistent. That's like a little bit pregnant. Mostly harmless. Typical pauses in the tens of milliseconds. That means there are atypical pauses that are a lot bigger. Okay. But what can we really do? Well, the first thing we can do is we can go crazy tuning. You adjust garbage collection, you have a bunch of parameters, you can play with them, you can adjust them, until you get a behavior that's acceptable, understanding that at some stage down the line, when your application and the data it uses and its interactions with the rest of the system change, it's all going to break and you have to go through that whole process all over again. It's a short-term measure. You can keep the heap small. That's what most of you do. That's what most everybody does. Lots of small instances instead of a few big ones. Take data out of the heap. Use an external cache. Use off-heap memory, which is horrifying. You can pull your objects. Basically, you do thread pulls, database connections. What you're really doing is building a custom garbage collector for that class of objects and hoping it's more efficient than the generic. You can commit ritual murder. That's the way the low latency guys do it. What they do is they have enough memory and they tune it so that it will garbage collect after 2 days and then they kill it every 18 hours and restart the instance. So they do a rolling execution of the running instance because that's cheaper to restart one and know that it's going to happen and not affect the data. Personally, I'm sort of offended by that, but. And of course, the other thing you can do is change the garbage collector to one that doesn't actually have this problem, which is what we do. Okay, here's why this is a problem. Here's the stuff you have to be able to do that existing GCs don't do. The first thing is you have to be able to do fully concurrent marking. You have to find all the objects that are in use, even though objects are changing what they point to, and just because it was in use a moment ago doesn't mean it's still in use now. If you do multi-pass marking, you go back and you try to look at the stuff that might have changed. You have a problem that if the application changes its pointers a lot, you're going to just keep doing that forever, and the overhead goes way up. You also have these things, these weak references and soft references and things that are really a challenge to work through. You have a problem with concurrent compaction. You're trying to compact, you're moving objects together to fill in the holes at the same time that some objects still have pointers to them in their old locations. And how the heck do you deal with that? The problem is not moving, the problem is making sure that everybody points to the right place. And what do you do if an application, part of an application is looking at a reference that is stale? There's a reference to an object, that object's not there anymore, it's either somewhere else or it's been collected. And if you can't do that, then we're back to stop the world where we need to do that remapping. And at some point, you're going to have to figure out how to do new generation garbage collecting when things are big. Because remember, we still have the problem that looking at live objects, think about it as a second per gigabyte. Unless our machines get, and our memory systems get a lot faster. And that's a reality. And as our heaps get huge, then even new gen is going to get big, and now we're going to have problems with new gen times 2. So we really want a new gen collector that can also work at scale, which probably means it has to be concurrent. Okay, so I'm going to keep this really brief because I'm not here to do a sales pitch. But this is what we do. We provide a Java virtual machine. It's Linux. It allows huge heaps. And it also has this idea of elastic memory where, how many people here have run into a situation where they ran out of heap space in a running application? And what happens when that occurs?
The application dies and you have to restart.
The application dies and you have to restart. We actually built in overdraft protection, where if the application runs out of memory, we have a separate memory area. We can increase the heap briefly. So for example, if we're garbage collecting while the application is continuing to create objects, we have to allow for the fact that it may be creating them faster than the remaining space. And so we can add to the heap so it has more room to create, and then when the GC finishes, it'll get back all that space and we can get it back. There's a bunch of performance monitoring stuff that we can do on production systems. This is all, I've talked about all this. These are the basic issues. So it's a concurrent, single pass marker. It's a concurrent compactor, really concurrent, not most of the time, not except when it isn't. The old gen is concurrent, and the new gen is also concurrent. They both do compaction. They both. It's not copying, and we don't have any code for doing a stop the world fallback. So. Remember this picture? Okay, so this is hotspot. This was parallel GC. And this was the same thing running on our JVM. Okay, so what you're seeing are the GCs that took place, because we're garbage collecting like crazy the whole time. It was exactly the same leaf size, exactly the same application code, just point job alone something different, and you get this. And remember, this was the, kind of the measured in terms of service levels, and there we go. So we actually had stalls because we had that, all the threads have to come together, so, first, occasionally that was 13.5 milliseconds. Okay, and this is really cool because this is the kind of thing you can do if you can handle large memory and don't suffer from it. So as I said, this was one of the Lucene guys, a guy named Mike McCandless. If you go to blog.mikemccandless.com, you can read all about it. And he took the Wikipedia index, and it basically was 132 gigabytes of index, and his heap was 240 gigabytes on a 256 gigabyte machine. And what you're seeing here, so the blue graph, now this is not GCs, this is transaction times. So he was doing 200 queries per second against that index, and the blue line is showing, these are percentiles, how long transactions took at that percentile. So the worst case was it took about 2.7 seconds at 200 queries per second on that box with CMS, concurrent mark sweep on hotspot. With us, you can see it wasn't much different than the average case. And then he decided to try with 400 queries per second, and so now it's up to about 8 seconds, worst case.
His data, though, is mostly like old gen or permanent gen.
Actually, no. Here's the interesting thing.
That's for sure.
It actually was mostly new gen. And the old gen, remember, CMS only compacts when it absolutely has to. He never saw an old gen compaction. He ran it for a couple of days, and he still never saw old gen. If he had, these numbers would be huge. Because to do an old gen compaction on a 240 gigabyte heap, you're probably looking at about 6-8 minutes.
Is it because he sized it like that, or is it?
No, it's because once he built the index, there wasn't, he wasn't creating garbage that lived very long. The queries were quick, and because they were quick, the space got reclaimed really quickly and it was back. So that was the thing, because he was fascinated. He could not get it to do a compaction. And just to finish up, I want to show you something that I think is really, really cool. And that is, so for the fun of it, I decided to run this EH-cache benchmark on all 3 of the garbage collectors that are part of Hotspot. And so again, this was the one with parallel GC. And then I ran it with CMS, and this is what I saw, which was absolutely fantastic until a compaction occurred, and then it was half a minute. And that's with a 29 gigabyte heap. Think about what it is with a 240 gigabyte. So the thing about CMS is it's really, really good until it has to compact, and then it's a disaster. And so, and it only matters if your objects are not kind of roughly the same size, and therefore it can't, fragmentation kills you. How many people here have to process XML? Yeah. Problem with XML is it's all varying size trees. Worst case for using CMS. And just in case you're curious, this is what G1 looks like, which was lots and lots and lots of GCs, but not taking massively long, 1.8 seconds, not quite 2 seconds. So there were lots of 2-second pauses, but nothing worse than that. And that's the thing. So, one of the things you have to figure out is, for each kind of application, you have to try them all and see which one behaves closest to what you want, and then you have to tune the heck out of it so that the stalls don't happen when they really hurt you. One of the interesting things I found out when I started doing this stuff with EH-cache, which is it's a benchmark they provide, and it reports on how long things take, and it lies. And most Java benchmarks lie. What they do is they say, I know that worst case is going to be awful, so I'm going to throw away the worst case. Or I'm going to force a GC before I start measuring, and another one after I finish measuring, and I'm only going to report the time in between. And what I noticed was, when I got to the point where the cache was too big a percentage of the heap, that's when I started seeing things really get slow and the numbers change. Because now the fact that it did a GC before and after wasn't good enough. It was forcing an old gen GC in the middle of the run. So that's why something like JHiccup is so useful, because it's actually showing you what it's really seeing. There is nothing hidden. It's telling you exactly what it saw, and you know that it's start to finish, it's exactly what a user of the application is going to see. Because in most cases, benchmarks are going to go, look, we know the worst case is going to be horrible, so we're just not going to tell you about that. There's nothing you can do about it anyway. And that's about all I really wanted to say. Oh, one last thing I did want to say. If anybody is curious, we have technical papers on our website. We do provide trials for commercial customers. I have some cards that give you a URL you can go to for that. Also, anybody who's doing open source projects, is, a committer to an actual public open source project, we provide free licenses to this thing. You can try it out on big applications. It's really designed for applications that can take advantage of a lot of cores, a lot of memory, want to do big heap kinds of things.
So
yes.
if I'm one of those 4 gig heap drives, so running your VM, what would be the cost versus the regular? That's the one. What am I losing if I use yours?
We're going to use more memory. We're going to use more cores because we're forcing things to run in parallel a lot. We're going to use more memory because we would rather use more memory, for example, for our card marking, so that we know the answer right away. So here's an optimization. They'd argue it's an optimization in hotspot, which is, remember how card marking, you have to keep track of every place outside of new-gen that's got pointed to new-gen? They use a byte per region of code. And then when they need to find it, they'll scan through that whole region of code, a region of data, looking for those pointers. We do a bit per word, because then we know exactly where it is. And then we can look at it and go, nope, not pointing to new-gen anymore, or yes it is, and therefore we have to follow it. So there's some stuff we do where we'll use more memory to get the efficiencies that we're getting. And it relates to the way we do garbage collection. So the difference is, yeah, so we're going to use more resources, but you're going to get consistent performance. More consistent than you've done.
A small JVM would have.
No, I mean, you're not going to run sub-gigabyte JVMs at all, and even, 2-4 gigabytes, I wouldn't bother. Unless you're seeing stalls even at that level, and then I would. But then you start thinking, it's like, and remember, one of the things you're probably going to save is you're not going to spend your lifetime doing tuning. You basically put it in place, and if we've done our job, it's just going to work. So, I mean, think about the time. How much time do you spend doing tuning on your JVM?
Me, 0. I have another guy doing it.
Okay.
A lot.
A lot. You do a lot. It's a lot of heuristic, kind of play with it and try things and change values, and they're never the same values between 2 different applications. There is no cookbook for doing this. You try stuff and you see if it makes it better or worse, and you adjust it, and of course, if the behavior of the application changes, you have to start all over again. Okay, well, thank you very much. And I'll take a few more questions if you like.
So for every core, every thread, application thread which I have running, how many cores should I set aside for parallel concurrent garbage collection?
I don't have a direct answer for that. The thing is, we're going to heuristically sort of lay it out. Are you talking about hotspot, or are you talking about what we do with?
Yeah, for your stuff.
With us, basically, we're going to use heuristics to decide.
So when I set up my machine, what heuristic do I use?
Okay, so I wouldn't worry so much about, you don't have to, you could lock threads to cores. The low latency people tend to do that, most other people tend not to, they just let it happen.
I'm just wondering what the ratio is. Do I really need a whole garbage collection core for every user application core generating garbage?
No. Oh no, absolutely not.
What's that ratio?
It's not a ratio. I would say you're looking at, you should probably think in terms of, I don't know, 4 cores for GC is not bad, 8 is probably reasonable. I mean, it's all a question of how big your box is. If your box is, say, 8 cores, then we're probably going to use 2, maybe 3. So I would make sure I had enough for my application to perform well, and then have a few extra for the GC.
So it can get up to about half of the cores.
Only if it's a relatively small box, maybe.
Okay.
I mean, with 16 cores, I don't need 8 of them for GC. I mean, with 16, right, if I have 16 cores, I do not need 8 for garbage collection, so it's a lot less than half.
So there's an upper bound. I'm really having a hard time grasping, because there's core. I can buy a machine with 64 cores in it. Do I only need 4 of them for garbage collection, even though I've got 60 generating garbage?
It's really going to depend on the application behavior, but it's going to. The thing is, we do a bunch of heuristics. For example, one of the things that surprises people is we'll force a full GC very early in the application's execution. The same way that Hotspot looks at how code runs and then changes its mind about compiling things, we're trying to get a sense of what the right numbers are. So it happens fairly automatically.
Okay.
So you don't tune it unless we absolutely, I mean.
Right, but at some point they're going to be competing for resources. If I have a 16-core machine, I put a dozen of my user threads on there, and then you fire up another 8 garbage collection threads, my machine's oversubscribed, and I'm going to get these big latency.
And basically what we're going to do is look at the number of threads and try to manage that so that things are not being solved. And we do have parameters that can be set. By and large, you don't worry about it. Just throw enough hardware at it and things don't run. Okay. Anybody else before we quit?
Is it useful for smaller, low latency applications? Assume that I want to guarantee no causes of more than 3 milliseconds.
Yeah, absolutely. I mean, the thing is that how big a heap are you looking at? Are you talking about? If it's a 4 gig heap, we're probably going to need more memory than that. We're probably going to need a slightly bigger heap than that just because of the overhead. But yes, we would get. So, for example, I know of one financial customer where we were seeing, they were seeing about a variance of about 22 milliseconds with Hotspot on a low latency kernel tuned machine, and we were showing a variance of 2 milliseconds. So yeah, we're probably going to need a little more memory in most cases just because of the way that we maintain data structures under the hood. So we're not. I mean, if they're running a 4 gig heap, we can try it with a 4 gig heap. I'm not sure it would run as well. But if it went up to 6 or 8, then we very well might. Okay. Yes.
So I know that reference counting systems are slower because the cache validation much more, but it's sort of like slower overall, and so it's sort of like having a consistently slightly slower solution is probably more advantageous for a number of transactional systems.
And yet Java didn't go that way. I mean, this didn't go that way. Smalltalk did. When you do GCs and things like C++, because you don't have the built-in support, you kind of have to do reference counting. One of the problems with reference counting is it makes all your objects bigger. So your granularity, you're not going to have objects that are the size of these, because you're doubling the size of them just to have the reference field. So, these are the trade-offs, and the Java guys went one way, and the Smalltalk guys went a different way. So, I mean, that's when you can argue. And it's Java made, they made that decision. Now, part of the reason they made that decision, I would argue, is because that's what James Gosling has done his entire career. He before he wrote Java, he wrote 2 other bytecode interpreters. He wrote Gosling Emacs, which has a Lisp engine, and he wrote something called News, which was display PostScript before Adobe had display PostScript. And then he wrote Java, which was originally written for set-top boxes and then for PDAs, and then became the web thing. And so he wrote it that way because that's the way he decided he was going to write it, and so that's why the memory manager has always been that way. But there are benefits to either side, and they just went one way, and it's a little like the big endian versus little endian religious war going as travels. That's where the terms come from, right? When you talk about big endian and little endian for bytes and words, it comes from the religious war over which end of a hard-boiled egg you're supposed to crack open. And so you had the Lilliputians who believed one way, and you had the other people who nobody remembers their names. I do, but no one else does. They were called Blefuscu, and they were the other side, and that was what the religious war was about, and that's where we get the terms big Indian and little Indian for starting at the left or starting at the right. I love stuff like that. And it's really relevant, but I had to share it. Okay, well, I think I've helped you.
One more.
Okay.
I happen to know.
I'm trying to let you go home or go get a drink or whatever it is you do.
I happen to know that AWS is currently starting to push not renting their bigger boxes, but to buy more small ones.
Mm-hmm.
And basically, and it wasn't about memory management. It's more about the redundancy and don't worry about the individual box speed to some extent.
But there are applications that just don't run well in smaller boxes.
That's what we had at the previous place that we had too, was for management, upgrading, you could get components and things like that, but it was not a financial.
There are customers. We talked to some companies, some fairly well-known companies who are using AWS and they're using the biggest instances, and they want bigger. They're not happy about how much it costs and the fact that the limit is what 60.5 gigabytes, and the cluster control instances just don't get bigger than that. But yeah, I'm sure Amazon would, because everything becomes interchangeable and having those big expensive boxes is. But there are applications that just run better in big boxes, and in the world, they're basically slicing up big boxes into lots of little virtual ones. It's not that the boxes are smaller, it's that they want to slice them up so they can sell them to even more people. But there are applications that really do well with big memory. And there are lots of reasons why people use this virtualized environments. But the idea that we don't need bigger instances is not one of them. Yeah.
How do you do on non-Java languages?
We do very well. If we find a problem, we solve it. We're working on the Java 7. By the way, the interesting thing about Java 7 is it has the first bytecode that Java has no use for. So we're working on that.
So do you support invoke dynamic yet?
Not yet. We will have it out early in the year, in 2013. We support the existing versions of Scala and Clojure with the work on Java 6.
How about JRuby?
Yep. Yes?
Yeah, I just had, possibly you mentioned this, but do you have support or have you examined these extensions for Java, like DPJ, deterministic parallel Java, that include concurrency? And
I really don't know anything about them. If they run in a standard JVM, then they should just run. Because we're using the existing Java runtime. We're using the existing Java libraries. It's just the JVM that we use. But I don't know anything specific about them.
so it seems like with all those processors, wide open for taking advantage.
Yeah, that's really true. Yes?
So, does Zing JVM supports operations that I can do on a regular JVM through unsafe class, like allocate the memory and manage that memory myself?
Yes, I believe we will. We need to have that discussion offline because I haven't really looked into that. What we do is we start with the hotspot source code, and then we modify the way the memory management works with the heap. We should leave everything else behind so that it just works, but I can't swear to that. I just don't know. But if that's an issue, then we have that conversation with you. A useful answer. Okay? Yes?
One more question.
Sure.
You already answered this. Why does Java have maximum size L?
What is it at? Why does it have a maximum size? Well, one of the things is that it runs very, very badly if you swap. So you want to allocate memory, and it wants to keep track of it. Basically, you want to know that you've got the memory you think you have. And that's sort of the simplest answer. But you can't just let it grow. out of bounds. And the problem, well, I mean, one of the things probably is because memory management does not, behavior changes pretty dramatically with scale, so you just don't want it to grow as big as the machine will allow it to, because you never get any kind of acceptable performance.
Is that still true in Zing?
What's that?
That you want to cap your overall memory?
Well, you want to cap it because okay, so here's how it works. What we do is, this is, by the way, the reason that we run in Linux and only Linux, is we have a device driver that lets us take control of the memory away from Linux. So when you ask, what you do is you configure this thing and you say, here's the memory that Zing is going to have for all the instances you're running plus the overdraft protection. And then we manage that separately from the OS. Now, one of the things this lets us do, which is really, really cool, is, so here's the problem. Garbage collector is running, application is doing terrible things to objects. How do we know that they're not hitting the same location at the same moment without watching every single memory address? And the answer is you just reprotect the memory that the GC is working on. So if the application tries to hit it, you get a fault, you know that that happened, you re-enable it, you get to tell the GC leave that alone for the moment, and as soon as they're out of each other's way, you let them run again. It's very, very efficient because we can do stuff that applications aren't allowed to do. That's one example. But that's the thing. So basically, when you install, you install this thing we call Zing System Tools. It's this device driver that goes into the operating system, and when you configure it, you say, here's how much memory I'm giving to all the stuff that Zing's going to use, and here's how much will be available to heaps, and it'll even say, okay, so you're giving overdraft protection this much, right? You can specify -XMX as big as this for a single instance. Now, if you run two instances, obviously they can't, they have to add up to that much. But that's the thing, so you can give it as much memory as you want, as long as you leave Linux open. So the example was, on my machine, which was a 48 gigabyte machine, what I found was, with all those cores, I needed to leave at least a little memory behind, and so I gave, I think, 70% to Zing, the other 30%, and after overdraft protection was taken care of, I had a 29 gigabyte heap max. And it told me that, and I said, okay, great. So it's pretty simple. But that's kind of the way we work. Yes?
Most of the applications that you deal with, big data, big iron server-side stuff?
It's, yeah. Up until the latest release, we really were just server-side. With the latest release, we actually can support things like the windowing toolkit, so you could do fat client applications and have all the release stuff work. We didn't support that up until now. There's historic reasons why that happened. But yeah, it is server-side stuff because it's big. I mean, although you know that you can actually get a laptop big enough to run Zing on. Dell has some laptops with 4 sockets, so you could actually get up to 32 gigabytes. Now the problem is they're probably only quad core, which wouldn't be that interesting. We'd probably run. Yeah.
Are any of the platforms as a service cloud providers utilizing Zing on the back end?
No. There are people using Zing on the cloud systems. I mean, we've got some stuff running on Amazon Web Services.
On the dedicated boxes?
On the cluster control boxes, the CC boxes, yeah. In fact, one of the reasons is that because of the memory management stuff, we don't run we run into problems with Paravert. We need the hardware virtual memory support, and those are only the CC instances. And whatever they call the ones with the extra graphics hardware, which are basically just CC instances plus the other stuff. We won't care.
I was just curious, I did a stint at Google, and it seemed to me that inside of the Google Cloud, as opposed to public cloud, Zing would be...
Well, but it's only if you're running Java, and then right where you are for those applications. So, yeah, not that I'm aware of, but I don't know. In spite of being in marketing, if I don't know, I make it up. Yes?
Yeah, I've got some use case with real-time Java. How do they do it in real-time stuff?
How do they do real-time? Well, there are a bunch of different approaches that have been done. The way it's done typically is use fixed object sizes. So they do fixed allocation of object, sizes for objects, which means you don't have the compaction problem. So it's much slower, it's much less efficient, but it's much more predictable. Thank you very much.